We'll continue our discussion on gradient descent convergence analysis for strong convexity, Lipschitz continuity, and then move on to better algorithms, accelerated algorithms, while providing motivation for why we want to accelerate. So we complete our discussion, this last pending step for Lipschitz smoothness and strong convexity, and then move on. So you could recap that we had this discussion with strong convexity where we made a couple of steps where we had application of Lipschitz smoothness, and yeah, without I've changed the color, by the way. Are these better? So, this is better, right? So I've made them all lighter now. Okay. So yeah, so we had packed everything together into this very important xt plus 1 minus x star is less than or equal to 1 minus mu by L, xt minus x star square, where mu by L is basically a strong bi-Lipschitz smoothness factor. And we know that this will always be between 0 and 1. Without further ado, I just recall that mu by L is expected to be, it will be between 0 and 1. In fact, it might be in the open interval 0 and 1. Okay, so we were not happy enough with this because we wanted convergence analysis in terms of fx star. Okay. So, however, we wanted analysis in terms of something like this: f of xt plus 1 star non-square. How do we get there? Well, we thought of using convexity at x star. Okay. Okay, we had this term already. So we combined smoothness and the fact that the necessary condition for optimality at x star is 0. So we combine smoothness and the gradient of fx star being 0. Okay, and this gives us this f of xt minus f of x star is less than or equal to L by 2 xt minus x star naught square. Okay, this is something we can always fall back upon, either through strong convexity or through Lipschitz smoothness. What happens very often is that we seek some relation between the difference of the functions and the difference of the iterates. And here you're seeing that we are able to bridge this gap, get an upper bound for the difference of the functions and the difference of the iterates using Lipschitz smoothness. And if you use strong convexity, you could probably get a lower bound. Upper bound using Lipschitz smoothness. Lower bound using convexity. I won't make it. Okay, so the next step is we'll make an assumption like we did before, that there's some radius, some circle of radius r that bounds the initial iterate from the optimal point x star. Okay, so this is our somewhere x star, and we are saying that x naught minus x star, let's say, is r square. This is x star here. So we make use of this r to further say that the right hand side here is bounded by r square. Okay, and this mu and L, you remember that they are basically the upper and lower bound on the curvature respectively. Okay, so we have basically the right hand side in terms of three things: R, mu, and L exponentiated by t. Okay, and this is what we kind of guessed. We get us log factor, right? So if I want my function value f of xt minus f of x star to be less than or equal to epsilon, how many t's would I need? Right? That would be of the order of log of 1 by epsilon. That's the next step. Okay, because everything else has now just become some function-based constant. Okay, so here we are. So there are only three constants here. One involving r, the other involving mu and L. Okay. So to get an error of epsilon, we need L by 2 into 1 minus mu by L the whole raised to t r square less than or equal to epsilon, which implies that t should be at least log of 1 by epsilon. I mean, a term with log by lambda or 1 by epsilon. Okay. How good is this? Let's try and now get the number of iterates. Any questions? So if you want an error of 0.01, we need only L by mu log of 50 r square L iterations. So the smooth and convex case, we needed 50 r square L. Whereas if you add strong convexity, suddenly things have become much faster. It's very interesting. A big difference that is made by strong convexity. The only difference between these two was that you have moved from convexity to strong convexity. Otherwise, everything else is the same. Okay. So summary. Let's look at so some abbreviation being used here. So if you have continuous, Lipschitz continuous with gamma is r by b square root t, some existential gamma. Could be other, I mean, even other gammas, right? Gamma equals this. This is basically the worst case gamma. This is for some intermediate inequality. So this we get an epsilon approximation in r square b square by epsilon square. Somebody had a question? But now look at how things have evolved. With smoothness, we got a 1 by epsilon. With smooth and strong convexity, we got log of 1 by epsilon. Right, and let's take some concrete case. We just take an L equals B equals 10. So L is the Lipschitz smoothness factor, B is the Lipschitz continuity factor, and let mu is the strong convexity factor, R is the radius. Just for illustration, these are constants. So strong convexity SS gives you and smoothness gives you 8.49 iterations. Takes you at least 8.49 iterations for 0.1 epsilon. And 13.49 for 0.01. So you have factored 10 degrees, but there's a constant number of steps, right? That's increased. This is a constant step increase. all right, and for a tenfold, tenfold higher precision. Was it tenfold? Yeah, tenfold. That's a lot. Right? That's a lot of gain, I mean. And again, tenfold, you find the same thing, constant. So 8.49 to 13.49, 5 steps, and then 5 steps you are basically 100 times more accurate. So practically, this is why strong convexity matters, and I think you've got enough of an experience now. I mean, like I'm just repeating the same statement. So I don't want to write this again. Okay. Any question? Whereas if you look at the other cases, right, it's like this is by a factor of 100. I'm sorry, this factor by a factor of, did I make a mistake? Yeah, by a factor of 100, yeah, squared basically. And the smoothness with convexity gives you a factor of 10. So this is into 100, whereas this is into 10. Okay. This is what is called linear convergence. So I could have gone through the gory details of what is a Q convergence, right? But you can go back. So please revisit the extra slides I gave on Q convergence, and understand this basically is Q linear convergence. Okay. Any questions? Okay, can we now do better with Lipschitz continuous functions? See, why are we interested in Lipschitz continuous functions? Very often we don't have differentiability. Hinge loss, you saw in your mid-sem, right? So, very often, especially in ML, right? With advent of different activation functions, ReLU, you can't expect differentiability everywhere, right? Cannot insist on. So but what if we have strong convexity? Now, how do we get strong convexity? Remember that if I add a regularizer to the hinge loss, I get strong convexity. Whereas that doesn't still make it Lipschitz smooth. You got this, right? So let me add to this point. So the first point means that we can't insist on this Lipschitz smoothness, but we could add a regularizer and get strong convexity. Okay, so this prompts us to really ask, well, can we do something better from an ML perspective? We probably wouldn't have asked this question for optimization in LinkedIn. So that's why we're asking this question. Can a function be both Lipschitz continuous and strongly convex? Well, we have seen that there is a problem, right? Unless you are dealing with some bounded region, you can't have this. Okay, so not always, but in a bounded region, it's possible. You remember this? We talked about this relation. I mean, I'm not going to take examples. So unfortunately, they both are not generally possible, unless, as I said, consider restriction. So what is the restriction on a bounded set? Right? And the gradients are upper bounded, gradients or subgradients. Okay, so, well, I mean, when we talk about Lipschitz continuity, then we're basically talking about the rate of change of function being bounded, and therefore subgradient being bounded. Okay, so suppose we have a bounded set. Can we do better? Right? Again, I'm bringing back the same question. So let's say my use case. Let's say is all of this with a bound or within a bounded set. What will that mean? It will probably mean that your parameter space is limited. If, say, let's say, norm W square is less than equal to some R square. Not a bad idea. I mean, you're just saying that some large value of R, it can be very large. So it is practical. It's not impractical at all. So let's say we have hinge loss, or let me be very specific, right? So hinge loss on say W transpose X plus norm W. Oh, I'm sorry, I should have had a comma Y plus lambda norm W square, and implicitly we put a bound that norm W square is less than equal to R. In some sense, when we put lambda norm W square, we are implicitly saying that there is a bound or there is a limited on how much the W should grow anyways, right? So it's not a bad idea. Okay, now we are getting greedy. Can we get an improved convergence rate in such a case? What do you think? Can we do better? What was the convergence rate we got? 1 upon epsilon square. So can we do better than that? So it turns out that you can get an omega 1 by epsilon. Was it? No, for Lipschitz continuity we got, with Lipschitz continuity we got 1 upon epsilon square. We got 1 upon epsilon for Lipschitz smoothness and convexity alone. Right? So we can do this apparently. How do we do this? Okay, so I'm going to recall. I want you to help me complete this. The colors are all okay now, right? So how did we get this first expression? Algebra, right? Then we use stronger lower bound via convexity. We had used strong convexity. I'm sorry. This is you are using strong convexity, by the way. So this we have not seen being used with the case of Lipschitz continuity. So this is we use this in the case of Lipschitz smoothness, right? Yeah, help me complete this now. So those in the class are working it out. I would request students on the call also to please try work this out. So how do I now take this to 1 upon epsilon? You can prompt as you proceed in progress. Can I assume something about gamma square, norm GT square? Oh no. Yeah, go ahead.
I'm just assume it is bounded.
Yeah, less than equal to gamma square BT square. And then what else can we do? The moment I say 1 by epsilon, then I cannot be as ambitious as earlier, right? I was basically getting an exponentiated form. 1 minus mu by L raised to T. I don't expect that here. I mean, I've got to resign to the fact that I've already told you 1 by epsilon is not be achievable. So we can work backwards. So how would you now deal with the last term?
We have mu into gamma less than 1.
Sorry, gamma less than 1.
Mu into gamma.
Mu into gamma less than 1. Why? Gamma is 1 by L. You are assuming gamma to be 1 by L.
Yeah.
Okay. So what we'll do is, yeah, let's see if we can persist without suddenly putting gamma to be 1 by L. See, we would like to put a gamma which, even in the worst case, honors certain inequality, right? So let's defer that, I would suggest. But what we can do is just get this into some quadratic form. We get this into the quadratic form. Anyways, what we could do is divide the whole thing by 1 by 2 gamma. So this, let's say I divide the whole thing by 1 by 2 gamma. Does that help? Let's try and get into this form. I'll just show this in the next slide. So I've done that. I've divided the whole thing by 1 by, okay, I've divided by 1 by 2 only, gamma. But you could do that as well. So, I have divided by 1 by 2 gamma. So I have brought this gray part to the left hand side. So notice that this component fxt minus fx star has come to the left hand side. And I have divided by 1 by 2 gamma. Sorry? Oh, there's a square here. Thanks.
I think now we can exploit the telescopic summation by combining the 1 by 2 gamma t on the right side.
Okay. Telescopic summation on this part. Right? 1 by 2 gamma, as you can notice, is there's a t here. I can probably do something to drop the index t, gamma t. But modulo that, you find that xt minus x star square and xt plus 1 x star square both have 1 by 2 gamma. So probably they can get cancelled. Good question. So let's try and do that. Can you try that? Sorry? So there's a question, what happens to this remaining part? Even if you do the telescopic summing and get away with cancelling some part, what about this part? Gamma won't be constant. So there's some reason I put an index subscript T. See, we're talking about existence of a scheme under which you get 1 by epsilon. So it's possible that I have to work harder than usual. It's possible that there's a choice of gamma for which this works. And that's why I said let's defer, right? Let's argue for why we need a specific value of gamma. Okay. So let me ask this question, will this disappear? Yeah. What's the value?
Specific choice.
Sorry?
I don't think we need a specific choice because the norm square is non-negative term and mu is also non-negative. We can just put another less than or equal to and exclude that term.
Okay. So the argument is that take gamma to be fixed, do telescopic summing, this part is anyways less than or equal to 0, minus mu by 2, whatever, right?
Yes.
Okay, so what happens then? What will you get? Let's try work it out. We'll have v square gamma t by 2 sitting out there. So that will be summed across all values of gamma t. Is that something we'll be bothered about? So this will be less than or equal to 0. I have another concern. This will be summed across all values of t. Yeah. You're saying v square gamma t by 2 should get cancelled with norm x square.
We just set gamma t at every time to t such that v square gamma t by 2 is equal to 1 by 2.
But this xt minus x star square. So suggestion was, can you set gamma t such that this term in blue and this term in orange now, they get cancelled out. That's a lot of knowledge. You need to know what is xt minus x star norm square. So good progress, but we need to take care of all these details. You can try and work out other schemes, but let me give you one scheme where you choose a particular value of gamma under which this convergence happens, which is also not bad. I mean, so let's do one scheme. So a step specific, t specific gamma t to make things work. Okay, you guys can think of all other alternatives. Okay, so far we are here, and now what I'm going to do is do something to get not only telescopic summing done, that we'll do obviously. That's very obvious. Next step, we'll have to do a summation, and then also set that these are two steps. So summation over what values of t?
0 to t minus capital T minus.
0 to capital T minus 1. Actually, using t plus 1. Yeah. 0 to t. I don't know what I've done in the following slides, but sum over sum in this is t. This and we'll use a gamma t, which is, so now gamma t, before we jump to some choice, what would you like it to be? Would you like to diminish? Would you like it to increase? Would you like it to increase, diminish?
Sir, diminish.
How would you like it to diminish?
1 by t, I guess.
Yeah. So gamma t proportional to say 1 by 2. And let's see if this that can help us. Okay, so let's take this value. Gamma t is 2 divided by mu into 1 plus 2. Same thing as gamma t inverse. So gamma t is 2 divided by mu into 1 plus t. And we have multiplied both sides by t. Okay, so now can you help complete? The reason we have put a t everywhere is just so that this term has t in the numerator and denominator. Doesn't really matter. So we're going to now start with summation 0, let's say. Also, let's do that also. The whole thing. So whole thing summed. What happens? Do certain terms disappear at t equals 0? Not everything doesn't disappear at t equals 0. The bu by b square value will remain, right? Okay, so let's write down the simplified expression. What will you get? In fact, this term will disappear for t equals 0 and t equals 1. This term will become 0. This term will become 0 for t equals 0. Yeah, this will also be what happens to the remaining terms? I mean, I don't want to write that long expression. So left hand side obviously we'll do a summation. Right hand side, can you simplify it for me when you do a summation? Let's try and write down the expression. So left hand side will be 5 t equals 1 to capital T. On the right hand side, what will happen? B square by mu. So sum it. I think I should sum it till t minus 1. No? That's how I've been doing. I don't have to do. Okay, so
b square by mu.
t b square by mu. So t into t minus 1 xt minus x star square will probably get cancelled with the previous.
Yes, so adjacent terms will cancel and will remain with minus t into t minus 1 norm of xt minus x star square.
Yeah. So all terms, in fact, as I said, this term will actually disappear for t equals 0 and t equals 1. So it will only be this term, the second term, that will remain until capital T, right? So I should just put a minus. Minus of t plus 1. Sorry, it's the summation 3 t minus 1.
I think t into t minus 1.
Into t minus 1. Are we sure so this will depend on? No.
Yeah, small t will be up to capital T minus 1. So
Okay, so t into t minus 1. Norm of okay.
into
Fine.
norm xt minus x star into mu by 4. You have the mu by 4.
Where is mu by 4? Of course, into mu by 4. Okay. Fine. So this probably is getting me up to a point. Now, what do I do with the left hand side? I mean, can I say something more about this also? I mean, this is a negative. So can I say this derivative is less than or equal to
Yeah,
b
tv
square
square
by
b.
b? Okay. So we are all fine so far. That's where we are heading. So I'm going to kind of this.
So I think we can lower bound the left hand side,
By
saying
what?
that f of x capital T minus x star will always be less than f of x small t minus f of x star for any t. I mean,
So
assuming x will decrease.
correct. So all the as iterates are proceeding, you're getting only smaller, right? The gap will also be reducing. That's expected. So therefore, you can upper bound the left hand side as well. That's what we anticipate next. Sorry, you can lower bound the right, lower bound the left hand side. But let's do that. So always try and write down the intuition first. You may often get wrong in our exact derivation. So intuition is lower bound reason, fxing matrix. Okay, let's move to the next slide. Are we all together? So I think I made some mistake here. This 70 minus 1. I just make these corrections. But otherwise it's the same. There's no difference. Okay, so let's now work on this further. This is where we all agreed upon. So now we want to work on lower bounding the left hand side. So what we observe, I mean that we would expect f of xt is less than or equal to f of xt minus 1 blah 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 less than or equal to f of x naught or x1 in this case. And of course f of x star is less than or equal to all of these. So if I just subtract all of them by x star, subtract f of x star from all of these, you will get 0 less than or equal to f of xt minus f of x star all the way to f of x1 not x2. So that's one thing. What's the other point? We now there's a t multiplication there. That should all this should help you take care of the second term, right? Let's say just put it in there. This term we can probably address. What do you do with t? The t being multiplied here.
We'll have something like this. So this will be lower bounded by summation over small t into f of x capital T minus f of x star. And we can take the difference outside the summation and then sum over t.
Okay, so suggestion seems to be that use this inequality and you will basically get this existing summation t. Okay. Let me. Using this, what we'll do, on the left hand side, we'll have t times f of x capital T minus f of x star is less than equal to this, right?
Yes.
And then
we can take the difference outside the summation.
this part has been reused here. And the solution is now we can just so this is greater than or equal to summation over t. As a summation over t is basically just t into t plus 1. Okay, so this is.
That will be, I think, summation over t equal to 1 to t minus 1.
Sorry, I've been summing over until t. Why?
No, because we started from 0 to t minus 1.
I see, okay. So we had t minus 1 on the right hand side. Okay, I think I just sum to t. I mean, it's okay, not a big deal. But then we would have got a t plus 1 b square, right? That was our answer. We would have got a t plus 1 b square.
Yeah. Yes.
The left hand side is t minus 1.
Yeah, left hand side summation is always still t minus 1. So in this slide, I think you need to change.
The previous slide I'll have to change it. T minus 1.
And here too.
In which case, it'll be f of x t minus 1. And that will be that lead to, yeah. Thanks for that correction. So t into t minus 1 by 2 f of x t minus 1. This is what you turn out to be.
I mean, we can even consider f of xt as well here. Because
yeah, actually it doesn't matter. So this part can be actually f of xt, right? This part. Because we have all of these less than or equal to. So I mean, it doesn't really matter. Let's do f of xt here. The multiplicand will become for t into t minus 1. Is this okay? Okay, so I think I made this small summation. I mean, I've done summation to t here. Yeah, I need to do a small correction in my expression t into t minus 1. Anyway, but I think pretty much otherwise it's the same. Okay, why did I have a t plus 1 here?
Should be t minus 1 as well, and the summation should also be a till t minus 1 again.
I'll have to make these changes. Okay, but these are really minor things. I mean, I think the order is more important, right? The indices, sorry, the exact factors you can correct. Okay, so this is a key. Okay, I'll make that correction here. So for error less than or equal to epsilon, we now need what? T greater than or equal to 2b squared by epsilon mu epsilon plus 1, right? That's the only difference, plus 1. Okay. So this is good. This is what we wanted, right? We wanted something involving 1 by epsilon and we have got there. Is that fine?
Yes.
This modulo is minus business. Okay. So now what does this mean? Well, this means that the behavior has now become similar to strong convexity and continuity. Right? Lipschitz continuity for strong convexity is giving the same behavior as Lipschitz smoothness plus convexity, which is interesting. So both the strong parts are smoothness and strong convexity are analogous in some sense. Where is that? CS. Okay, but I have used some different factors here. Wait a second. S and CS. Yeah, okay. They are the same thing, same order. These two, let me just draw your attention. So this is 1 upon epsilon and so is this. So CS and S behavior would be similar. Okay. However, the exact times are going to be different, obviously. Exact times would also depend on, other factors. But it's interesting to see that in both cases, we are, as you want 10 times more precision, the amount of time required is going by the same factor 10. However, with smooth functions, the time required is generally less. Yeah, so this is the smooth function case. We got generally 50, 500, 5,000. So smoothness gives you better overall time, but that's an empirical observation. Just I don't want to confuse you. Make a side note. This dependence is still like 1 upon epsilon. Otherwise, it's same overall. Like continuing strong convexity, XCS. Okay. Now, can we do better? We are now getting greedy, right? All this is whetted our appetite. However, there seem to be some interesting lower bounds with convexity, which basically tell you where you'll hit the wall. You can't do better. So, let's understand these. Lipschitz continuous functions. So far, we have found this gradient descent RV by square root t. Right? That's what we know. That's basically 1 upon epsilon square. This is the same thing as saying we got a t greater than or equal to 1 upon some alpha times 1 upon epsilon square. Right? But it turns out that actually any black box procedure which does descent, gradient descent, will have an error of at least what is provided here in red, RB by 2 into 1 plus square root t. So that can be proved. Oh, so looks like it's not bad. I mean, what we have found is not a bad at all, lower bound for the time at all. Omega basically, right? Let's look at the other. I'll talk about how these are proved in general, but let's understand the other cases. Again, gradient descent for Lipschitz continuity and strong convexity, just now it gave us something like this. There was a minus here instead of plus, that's okay. So 2b square divided by mu t minus 1, right? Now it turns out, okay, and this basically also meant that T was greater than or equal to alpha times epsilon. And it turns out that the black box procedure will have error of at least b square by 2 mu t. So which is of the same order. I mean, that's again very encouraging. Case 3, smooth functions. Now here there's a slight scope for improvement. Okay, and all our attention is on this third use case. Okay? Because we are now seeing a gap. What's the gap? This all eyes on this. And you know that's what will motivate our next step. Any black box procedure will have an error of at least some constant into 1 upon t plus 1 square in the denominator. Whereas what we got was LR square by 2t. So that's a big difference, right? We can actually do faster. So there's a gap between the lower bound and actual time. Can there be an improvement? Yes. That's exactly accelerated gradient descent. Okay. Case 4. So smooth plus strongly convex function. This is what we did. Started pre-midsem, concluded before midsem, I mean just after midsem. So let's say kappa is L by mu. So what do you expect kappa to be? Greater than 1 or less than 1? Kappa will be greater than 1. Okay, so then any black box procedure will have an error of at least square root kappa minus 1 divided by square root kappa plus 1, the whole raised to 2t minus 1. Okay, raised to 2t minus 1 again looks very familiar, right? Because we had a similar kind of overwhelming experience. We were very happy to see that gradient descent gave you this, you know, L by 2 kappa minus 1 divided by kappa raised to t. Now it's 2t minus 1 versus t. Is that a big thing to be worried about? In exponent. Sorry? Yeah. So the kappa minus 1 divided by kappa is also, you put the square, take a square of it. So there's nothing much to be worried about here. Okay, there's no gap per se. Okay, I'm going to quickly run you through how these get proved. I mean, I don't want to again get lost and overwhelm you. So let's just okay, so this again a reference here, section 3.5, page 53 onwards of a particular archive document. This is by Sebastian Bubeck, dimension-free convex optimization. That's a chapter. So he says that we prove here various Oracle complexity lower bounds. His results appeared actually in some other paper, Nebraska and Newton. But then this is slightly simplified presentation. You might find Nebraska a little difficult, but then there's another presentation from Nestor. Now, what's the proof procedure? Take any of these to show that you will take at least so much time, right? At least this much time, at least this much time. You just have to cook up a function. Okay, that requires a lot of hard work. What is that function for which you will get at least so much, time? Let's see some examples. So the proof is for this, we consider the following alpha strongly convex function, and this is a function. So fx is gamma times max over some indices I between 1 and t of xi plus alpha by 2 norm x square, and so on. And for this is obviously not differentiable everywhere, so sub-differential, basically a subgradient is computed. So I will in fact talk about subgradient algorithms as well. But the point is, it's all existence of a function. Let's take one more example. Again, this is an even more contrived, complex function. So existence is just by showing that there's a function for which you will take at least so much time. So for each case, there's a different function choice. It's not that the same function will work everywhere. Like here, exactly this, the last one we dealt with, kappa by square root kappa minus 1 divided by square root kappa plus 1, right? So there's another function here. Okay, so it's something in terms of inner products plus norm x square. Okay. So we won't delve into these, but the reference is given. How exactly we prove. Now, we spent some time on accelerated gradient descent because that's also used extensively in neural networks. The whole concept of using momentum, it has come from acceleration. And the class has also been innovated upon because of the gap. So it's important to understand the genesis behind these algorithms, which probably are being served on a silver platter today through different, not only algorithms, but also the implementations, which we don't even often peek into. Okay. Is this clear? Can I proceed? Any questions on this? Okay, so the moment the question is, accelerated, then my question is, why do you have to accelerate something? Something must be slow, right? So what's the motivation for acceleration? Any thoughts?
I think because of the gap, because of the more gap that we have.
This gap, yeah. So that's like that's one motivation from the point of view of time, right? What is possible and what we have got to. Maybe Nesterov or whoever tried to prove could have come up with another function for which the time would have been LR square by 2t. Error would have been LR square by 2t, right? So maybe they didn't come up with the best function. They came up with an easier function. I could argue that way, right? So just because there's a gap doesn't mean that it's a motivation, but it's not sufficient. It's probably necessary, but not sufficient, right? So thanks for that suggestion. So let me go back, right? So, huh? May not be. Yeah, it's just existence of one function for which you have shown that you have shown that it will take at least so much. The gap will be at least so much. The gap would have been large for some other function that this is a motivation one, bridging the gap. And what the counter I'm trying to provide is a concern. Okay, so I don't think this is good enough. We also need a little bit of intuitive motivation. What's so you had some intuitive motivation?
If the gradient at a particular step is very large, then we could use that to make an increase to the
So the suggestion is that if the gradient at a particular step was very large, you could have,
like instead of keeping the gamma constant,
instead of having this gamma multiplication, you could have adapted that gamma, adapted how much you should step. So question is it only about the gamma step size along that direction, or is it the direction itself that could have been different? See, gamma we could do using line search, which we have kind of brushed under the carpet. We'll probably do after our other algorithms towards the end, line search algorithms, which are important. But it's not just about step size, right? It's also possibly the direction that's too myopic. What if the smoothness and strong convexity try to look at curvature? Could we get a surrogate for the curvature from the previous iterates? How are these proceeding? Okay, let's take this example. So, motivation 2, empirically, could the next iterate have been influenced by the series of previous iterates? Also, which also account for some curvature of the function. And here again, I want to point out, we are not only talking about, when I say iterate, it's both the step size and the direction. Okay, let's take this simple illustration out here. Um, what you see here, right? Here, basically, should I zoom into it? This is easy to see. So what we see here is the gradient is a direction here. So it's moving here, and then the next step it realizes, oh, because it's looking at local gradient, right? Because direction of steepest descent in the gradient is going up here, down here, then up here. You see a lot of oscillation. Now, if let's undo this. So let's say I had this historical move, and I'm somewhere here. If I let's say I moved in this direction, okay? So I moved in this direction, and here I was moving in this direction. So could the iterate here have benefited from the fact that I already moved down? I'm trying to just compensate by moving up. On an average, maybe it's just saying go forward, don't go up and down. Right? So if you take these two together, you just copy this, these two, right? Let's look at what the average of these two would be. Like. What will it turn out to be?
Somewhere in the middle.
Right. So average movement. So maybe all they are confirming is that there's some small movement in this direction, right? Maybe in this direction. So the components vertically and horizontally are getting cancelled out. There's only a horizontal movement. So could we have done this more principally rather than just randomly pick 2 points? I mean, what we have done is just pick some historical point and cancel it out with the current point. But I could have done this at every step. Okay, so so this is exactly what this average movement is, what we are referring to as momentum from the progress made so far to push it faster towards the optimal. I mean we know the optimal basically is this point, and why am I beating around the bush? Why can't I just go there? Okay, so that is accelerated gradient. Now there are various versions here. Okay. So there are some efficient alternatives, and exactly what I showed in the previous slide, I'm again showing it here. But I'm giving it some different names. So gradient is what I had computed at the current iteration, right? So this is gradient. But to that, I'm adding something called velocity. Velocity is what contributes to momentum, all of us know, right? So the previous, I had this momentum, this average movement is the direction of momentum. So how about explicitly accounting for that velocity and adding that to the gradient? So basically it's like saying x actual, there's the actual step here in blue here. X actual is the old version plus velocity. So old, sorry, yeah, old is the previous iterate. It doesn't have to be in, I should have put it in blue. But B is the one in green, right? Where B, which is what this is. B basically is saying I look at the momentum, some alpha times momentum, and the current gradient state. So that's possible. Now the velocity itself, okay, so what I'm trying to tell you is that the velocity itself could either be by accounting for the current gradient or not for the current gradient. And we'll talk about it. But let me write down what exactly you see here. So you see this multiplicative factor, alpha. Okay, so what you see as alpha is multiplicative. Um, how much of the previous history to take, how seriously to take the previous history. So that is being captured through this multiplicative factor alpha. Is that fine? So yeah, think of this V, this is the update. The velocity is in some sense accounting for the momentum. So more specifically, this is the momentum. I mean the V is velocity, but this is the momentum. Alpha V I is where the momentum is coming in. Minus, actually you can drop this Vi. This entire thing is a momentum. Minus what the current gradient step has to say. So this alpha, what would we expect? Would we like to keep alpha increasing, decreasing? Should be greater than 1, less than 1? Because I've used this keyword multiplicative factor. What's your opinion? What do you expect alpha to be? Should alpha be greater than 1? Should we ever allow it to be greater than 1? Should alpha be less than 1? Can it be less than 0? Okay, so alpha between 0 and 1 makes more sense. In fact, strictly between 0 and 1. So history has to fade away at some point of time. That's what he's just saying, right? So neither of these. Okay, so let's proceed. So V plays the role of velocity. It's the direction and speed at which the parameter xi moves through parameter x. This x I used. I've dropped I here. Parameter x moves through the parameter space. So there are two things being captured here: the direction and speed. And as I already hinted, there's an exponentially decaying average of the negative gradient. Okay, and basically you have a decay factor alpha, which is between. So alpha can be 0. It can be 0. It doesn't have to be greater than 0. Which means that you may not care for any of the momentum. We did care for momentum so far. We didn't really, look at the trajectory so far, right? So we could persist with that. So these are common values of alpha: 0.9, 0.5, 0.99, and so on. And yeah, given a physical analogy, negative gradient, which is a force moving a particle through parameter space, according to the Newton's laws of motion. So gradient is contributing to the force, and then you have a momentum coming from the previous iterates. Both of them actually in some sense are reflected in this velocity component. So when is the step size largest? When would you have a large step size?
When the gradient and the velocity are in the same direction.
Right. And when will the gradient and the velocity kind of be in the same direction? When would you expect them to be in the same direction?
Close to the minimum, global minimum.
No, I don't think that is it. I would say let's not even talk about global. We can even say local. So the first suggestion is that step size largest when the gradient and velocity are in the same direction. More generally, when? Can I talk about successive? Something like successive. So far, what's been happening? It's not just the current trend, right? Not the current velocity and gradient, but all the previous also, right? Well, should I say successive velocities or successive gradients? Velocity is an outcome of the gradient, successive gradient. So, won't it be correct to say successive gradients? Does this make sense? Okay, so I've drawn a figure here. You can see all these updates were in the same direction. The gradients were in the same direction, right? If you're trying to reach this point, let me show this specifically here in this ellipse solid. So let's say I was moving on. Anyways, so I'm trying to show this here. Okay, here. If you're here, if you're along the major axis, so I can zoom in. If you're along the major axis, then I would expect this, right? They're in the same direction. The issue is when you are not along the major or minor axis. If you are at some other point, then we would have expected some amount of misalignment. Is this clear? So now, there are multiple alternatives even here. What are the alternatives you can think of? Sorry? Alternatives for implementing momentum accelerated gradient descent. Okay, so you see that I have not specified whether this x is old or new. I mean, I put it in red, but it could have been this x actual or what x new, whatever, right? X new. When should I be computing the gradient? After the update or before the update? Do a velocity update and then compute gradient, or compute the gradient and then compute the velocity update?
I think first we need to compute the gradient and then check the velocity and then go in the net average direction.
Okay, so as per this figure is doing exactly what you suggested, right? So this figure seems to compute. Sorry, this figure is computing both gradient and velocity at the same step, right? What you are suggesting is compute the velocity and then do the gradient, correct?
No, I'm suggesting compute the gradient first and then find the velocity.
Okay, so you are basically saying this, right? Your suggestion is exactly what is shown in the figure here. Right. So option 1 is that the gradient compute at x pole, right, and then velocity. There is also option 2, where you could compute with respect to the new, actual new whatever, right? I mean, let's just call it new. Okay, so these are different alternatives. Both have pros and cons. I don't think we can argue one is always better than the other. Okay, so these are two different this is a momentum update which we discussed. Here, okay, let me show the two options. Option 1 is exactly this. Option 2 is what is update, what is being executed in the so-called Nestro momentum. You compute the velocity at the current step, do update, and then compute the gradient, and then you compute the actual step. So the x new, I mean, I didn't call it x actual for obvious reasons, because x actual will only be after you compute the gradient at the new step, right? So this this kind of intermediate point is my x new. This makes sense. So there are names also. This we call it momentum update, but this has a name on the left-hand side. It's called the heavy ball or the Polyak update. That's the one on the left. The one on the right is called Nestero. The same Nestero whose name we came across with respect to that tight bound proof. Okay. Can we move on?
Yes.
Okay. So this Nestero, which we talked about, it turns out that for the specific case we talked about, it can speed up rate of convergence from order of 1 by t to order of 1 by t square. The error basically. So this is the one on the left. The one on the right, sorry. The Nestero momentum. And let's just quickly understand what it's doing. Xt plus 1 is xt minus mu of xt minus 1. That is the velocity part, or rather the momentum part. And then the gradient is computed at xt plus mu of xt minus 1. Right? So we are basically doing the momentum update, or no, velocity, velocity update, computing the gradient after velocity update, and then adding that along with the new momentum or new velocity. This is a new velocity, mu t minus 1 is a new velocity to xt. Whereas here you are computing the gradient at f of xt. So here see, look at this difference. Okay? Just want to draw your attention to this difference. So here you have minus alpha times gradient of f of xt, and here you have minus gamma, so gamma alpha, that's okay. The gradient is not at xt, but at the momentum updated version of xt. Okay, and this is what I was referring to as the x new. Okay, so that's one big difference. In both cases, you are adding a momentum, mu t, so mu of xt minus 1. That's being added in both cases. Right. Under the conditions, so I mean these are under the conditions we talked about, which is Lipschitz, the last case, right? Lipschitz smoothness and Lipschitz continuity and strong convexity, which is often easier to get. You can add a regularizer to a non-differentiable function to get strong convexity. but it will not be Lipschitz smooth. It's Lipschitz continuous on a bounded range. Okay, so this is the main difference. Okay, so let's try and understand these algorithms a bit more. This basically is the intuition. Um, okay. So again, I want to bring out. So it's not, Polyak is always bad. Speeds. I just want to bring this again because you might think this Polyak is. Then why did Polyak waste his time? Or right? I mean that's not the case. This is for Lipschitz continuity and strong convexity. Only in that case. Otherwise, there are other cases where it will work well. I mean, why do you think? So, since we are on this, maybe I want what may be the intuition? Why do you think Nestor momentum might work well when you're looking at strong convexity and Lipschitz continuity? So my observation is that the modified Nestor momentum, the one on the right hand side, gradient is evaluated after the current velocity is applied, and that leads to some speed up. In the case of Lipschitz continuity and strong convexity case, why do you think that might be happening? But what is the specific connection with Lipschitz continuity and strong convexity?
I think by taking a step in the direction of velocity before, we are sort of expecting the curvature of the loss function, and maybe there it is going to the case where we have Lipschitz smooth. I think that's why we are getting that 1 by t square.
So we are more aggressively exploiting the curvature. Is that the intuition? More aggressively. I mean, even Polyak is trying to exploit curvature after all. Momentum idea is to exploit curvature, but more aggressively exploiting, right? Okay, so here's the idea. So let's do Polyak, the one on the left. Okay. It's called heavy ball. Okay, so it turns out that it's not a bad idea, by the way, for strongly convex plus smooth. If you have strong convexity and smoothness both, then Polyak is also okay. Because both of them are kind of strongly convex and smooth, both have curvature bounds, right? So, I mean, just by your intuition, right? Again, don't write this in any exam or any paper. But the intuition is that Polyak is more heavily exploiting, Nestorov is very heavily exploiting curvature. Polyak is being a little conservative, exploiting but a little conservatively exploiting. So if you have strong convexity and smoothness both, then you have to be a little careful, right? You have upper bound and lower bound both on curvature. You remember? So this function, and you have so if I had so this is what the bounds we understood to be, right? So in this case, strong convex and smooth, we have both an upper bound and a lower bound in the curvature. So we might have to be a bit careful in going aggressively in exploiting curvature. And looks like Polyak is conservatively exploiting. Okay, why? Let's again look at it. standard gradient descent. These colors are all visible, right? But the red one possibly I should have put. The others are all fine, right? So standard gradient descent was xt plus 1 minus xt is xt minus alpha t gradient xt. Now inertia is saying, okay, xt plus 1 is xt minus the gradient at the current rate plus the momentum. Okay, so momentum is exploiting the curvature of momentum or velocity. Empirically, it's only exploiting the curvature in an empirical manner. But here, the second component in Polyak, there's a conservative exploitation. Okay, so whereas in the other case, we'll see that that term also starts exploiting. So overall, we have conservative exploitation. That's the key. Yeah. Yeah. So aggressive might be a problem because your strong convexity says that you have at least so much curvature, and smoothness says you have at most so much curvature. So you're basically putting a kind of there's a tunnel around which your function can change, right? So you're saying, okay, I'll overexploit curvature might be a little challenging there. So it's a very intuitive explanation. I mean, I think we should not discuss this further, just so that you remember. That's all.
But on Nesterov, on the other hand, we have the lower bound.
Yeah. So Nesterov, that's what we want to see. Nesterov for Lipschitz continued and strong convexity, which is only looking at strong convexity curvature, right? It is better. I don't remember, but I think Polyak does better for strongly convex and smooth. So, and what is the result? The result is that it converges in r square by 2 1 minus 1 by kappa raised to whole raised to t. Whereas, if you can compare it with what gradient descent was giving you earlier, so we have 1 minus 1 by kappa raised to t. Right? This is so certainly. I mean, there's not so much difference, right? Do you see a big difference per se? Smooth and strongly convex functions. It's doing pretty well. What I'm trying to say is it's doing well. It's not certainly worsening things. Okay, but let's look at. Okay, now we look at the other version. Okay, I think we're running out of time. Oh, we already are running out of time. We'll continue on this in the next class. Yeah, we can continue this discussion next time. So I didn't realize the time. We'll start with your question about the square root p, right? Thanks.